What is the minimum value of the force F applied to move a sphere, ball, circle, weighing 20 newtons from a ladder as shown in the figure below? Okay. And then it gives us possible answers. Okay. Also looks good. So what I'm going to assume here, so this ball is pushed up against this corner right here. And so when we're talking about movement, we're basically going to talk about forces. But in this case, forces usually talk about translational back and forth. What's going to happen here is we're going to put a force on this ball, and it's going to cause it to rotate. And we're talking about rotation, we're going to be talking about torques. And just like the idea is you're going to get motion, i.e. acceleration, when you have a sum of all forces that's not equal to 0. Likewise, with torques, you're going to get rotation when the sum of all torques does not equal 0. So that's where we're going to start. I'm going to say the sum of all torques equals, and there's going to be some force. I'm just going to draw some random force here. Force pushing it. And then we're going to have another force. I'm going to call this force G for force gravity going down. And so torque is R cross F, basically the pivot arm, times, so there's going to be R, I'm going to call this just RF, or R of our generic force, cross F, which is our force, and then I'm going to subtract from it R, and I'm going to call this center of mass, because it's the force of gravity we're going to assume is acting on the center of mass, cross, and then we're going to do force of gravity. And the reason I subtracted this is that subtraction sign just says that it's torquing in opposite directions. This force is causing it to go up the step, while this force is causing it to go down, or basically roll down the step. And this negative sign basically just says that they're in opposite directions. And I chose the positive to be up the step. I just have to keep that in mind. Now, we want it to just barely move. So we have minimum just to start it to move. So we're going to look at the forces where it's just perfectly balanced and then say, this is the minimum, anything above this will cause it to move. So we're going to say the sum of all torques in this case is equal to 0. All right, so now we got that down. I'm going to rearrange these slightly just to make it more palatable, enjoyable, something to aesthetically pleasing. RCM cross FG. All right, so we got these. So we want the minimum force. So this right here is a cross product. Cross product is a measure of how perpendicular two vectors are. You often see it seen as the magnitude would be RF sine of theta, where when theta is 90 degrees or pi over 2, then it's maximized. And when theta is 0, then it's minimized. And the idea is if you have two vectors that are perpendicular, pi over 2 apart, then they're as perpendicular as they can be. If they're parallel, theta is 0. Therefore, they are not perpendicular at all. They are the opposite of perpendicular. They are parallel, which is why sine of 0 then would be 0. So to maximize this, we want theta to be 90 degrees. And so R, our moment arm, is going to look like this. So it's going to be straight from our pivot point to where our force is, and then this force is going to be perpendicular to this moment arm. And since this is a circle, or a sphere, or a ball, etc., round, it's just going to be tangent. So this right here is going to be 90 degrees. So this RF, our tangent arm, is actually just going to be the diameter of the sphere. So I'm just going to call that 1. Specifically 1 meter or 100 centimeters, which is 1 meter, which is convenient. And then I'm going to say that this theta here is 90, therefore this is also 1. And therefore this side right here is just going to be F. Really it's F times 1 times 1. But you get the idea. It's F. And that's going to be R times cm. So this is going to be the radius to the center of mass, which is going to be 0.5 meters, or 50 centimeters, or 1/2. This is going to be force gravity, which they already give to us up here, which is 20 newtons. So we don't have to do the mass times gravity. We're just like, oh, 20. Convenient. But now we need to do the theta. So I'm going to redraw this picture right here, just to be a little bit more convenient, maybe slightly more to scale. So we have something like this. And this is 0.5, this is 0.2, which means this right here is 0.3. And so we have kind of this triangle right here. So we have the force going down, this is force gravity, and we have our moment arm. And I'm not really concerned about the direction of the arrow, forwards or backwards. It's fine. It's important, but that'll have to do with the sign that we're using, and we already took care of the sign by having the negative up there. So I'm just worried about magnitude at this point. This right here is going to be 1/2 or 0.5 meters. And so if we look at this triangle right there, we have a triangle that looks like this. So this is going to be 0.3, this can be 0.5, and therefore this angle right there, we'll do SOHCAHTOA. Tangent is opposite over adjacent, tangent of theta. And this theta then is going to be the arctangent. I know my handwriting is terrible, and I apologize. Opposite, which is 0.3, 0.5, and then we're going to go to Wolfram real quick. So we'll do arctangent of 0.3 divided by 0.5, we get 30 degrees? Maybe it's 30. No, yeah, actually 30. I'm going to call this 31. I'm going to go with 31. So I'm going to say this is kind of sort of 31 degrees. But we don't want theta. We want what I'm going to call phi right here, which is this angle right here, which is the angle between the moment arm and our vector, our force gravity vector. So I'm going to call this phi, which is going to be 90 minus theta, which in this case is going to be 59 degrees. All right, so now we got it. So we were looking for this magnitude here. R, center of mass, cross FG, the magnitude of that is going to be R, which is 1/2, force gravity, which is 20, times the sine of the angle between the two, which is phi, which is 59 degrees. So I'm going to do a little simplifying here. Kapow, 10. So I'm going to do sine of 59 degrees. Sine of 59 degrees, which gives us, let's say 8.5. So 0.857, which is 0.857. 10 times 0.857 is 8.57. And this is, I'm going to move these to the other side here, but they're both 1, so all that's going to affect is the units. So the minimum force is going to be 8.57 newtons, because up here it's actually like, I think Newton meters. But when the units work out and we solve for force F, our mystery force, we just get 8.57. And so that should be our final answer, which I'm going to round up to 9. And so to kind of backtrack what we did here, we wanted to know when this ball started moving. Since it's already pushed up against the wall, we're going to look at rotation. And since we're talking about rotation, we want to look at sum of all torques. And we want to do the minimum, we want to look at when it just starts, which says equal to 0. So it has to be greater than 8.57. I could actually say like 8.58. It doesn't matter. You get the idea. And then we just start plugging in values. So other thing we want to do is to have a minimum force. We want to maximize R, which means we're going to use the furthest distance we can, which in this case is the diameter. And we want to maximize the cross product. And to maximize that, we want to maximize the angle between the two, which is 90 degrees. Plug those in. That way we can minimize force, solve for F, and there we go. So I hope that helped. See you next time.